We humans communicate in natural languages. However, these languages are subtle, they are ambiguous, they are not appropriate for the precise specification of an algorithm. When we communicate our instructions to a computer, there should be no ambiguity on how the computer should solve a particular problem. So then, how do we write software? We have come up with different kind of languages, which we call programming languages. There are three broad categories of programming languages: high-level languages, assembly, and machine languages, machine code. The machine code is what the computer as an electronic machine understands. The machine language is just contains instructions that are series of ones and zeros. In the assembly language, the instructions are words, however, there is an one-to-one mapping between an instruction in the assembly language and an instruction in machine code. Now, in high-level languages, we say that we can write complex statements in the sense that a statement in the high-level language will be translated into many statements, many instructions in assembly, and therefore in machine code. So the instructions in assembly language and machine language, they are very simple. In a high-level language, they are more complex, and therefore we as humans find it easier to write our programs in a high-level language. The translation, however, to machine code still needs to happen somehow. Compilers and interpreters are those programs that will make this possible. They will take our code, which is written in a high-level language, like Java, and will translate it gradually to machine code. Now, how about the more specifics? How do we actually write our programs? What kind of tools do we use? The most common way to write software these days is by using integrated development environments, IDEs. In these environments, we can edit the program, edit the code, and also compile, run it, and debug it if needed. Examples of IDEs include Eclipse, NetBeans, and IntelliJ IDEA. Now let's look more closely on how the translation actually happens. We mentioned that the compilers and the interpreters, these programs, are the ones that are performing the translation from the high-level language that we are writing our programs to the machine code that the computer understands. But how does it happen? The first diagram that you see on your screen shows what we call static compilation. The compiler takes the program that we have written in the high-level language, say a program in C, and translates all of it into the equivalent machine code. After that step, we can take the compiled result, the program in the machine code, and execute it on that particular machine for which the compilation happened. How are things different with an interpreter? The interpreter will not translate all of the program at once. It will take chunks of the program, it will take a statement, for example, translate it into native machine code, and execute it. After it has done that, it will go back to the high-level language program, take another chunk, another statement, translate it into native machine code, execute it. Then again, it will repeat that until it has reached the end of the program. This is called interpreted execution, this kind of model. Now, there are pros and cons in both approaches. For example, with static compilation, the resulting machine language code is usually faster. It is usually better code than the one that the interpreter is going to produce, mostly because the compiler, since it knows all of the program before it actually translates it, it is also capable of doing optimizations that the interpreter cannot do, because it has to translate and execute a statement before it sees what comes next. Static compilation also has the privilege of hiding the way the code works. It prevents people from illegally copying or modifying the code. Licensed software like games, for example, is a common target. People try to modify the code so that they skip around the license check or so that it makes them better players at a particular online game. On the other hand, with an interpreted language, we can have more portability. Remember, the code that the compiler will produce will be good only for that particular machine for which it compiled it. If we want to run the same high-level program on a different machine, then we would have to compile again, because the compiler will then produce different machine language program. With the interpreter will directly translate and execute on the CPU of the program. So there is more portability. Now Java tries to combine the best of both worlds, and it does the following. The high-level program that we have written in the Java programming language is going to be compiled. However, the output, the result, will not be the machine language program. It will be a low-level program, but it will be platform independent. And we call the output bytecode. We can have many different machines to which we will transfer this bytecode. However, each of those machines will have its own Java virtual machine, a Java virtual machine which will be specific for that platform. And part of the JVM, the Java virtual machine, will be the just-in-time compiler, which will take the bytecode and it will produce the equivalent program in machine language. So Java, what it actually does is that it does most of the compilation of the high-level program into one step, producing the bytecode, but it leaves all of those segments that will need to be translated into a machine-specific way for last. This is why we call it just-in-time. It is at the very last moment that we're going to translate those machine-specific elements into machine language.